So let's use Newton's method of approximation to determine an approximation of the equation x equals cosine of x. But as you saw visually, this is a game of playing with approximating x-intercepts to the graph of the equation y equals f of x. So if you don't mind, I'm going to rewrite this. So bringing everything to one side, I don't care which. There is the equation for which I'm going to find an approximate solution. So we will let the output of my function f be this mess, and let's you and I pay the consequence of our actions. But doesn't that imply that the n plus first approximation is its predecessor minus the ratio of f evaluated at that predecessor to f prime evaluated there? And I think that in particular means this. Now, everybody, I can't just stop here. I've got to start with an initial guess. Notice how if x is, I don't know, something easy like 1, the left-hand side's 1. The right-hand side is not, but it's close to 1. The cosine of 1 radian is close to the cosine of 60 degrees, which is somewhat close to positive 1. So if you don't mind me saying, I think a reasonable initial guess is by allowing x be equal to 1, or x sub 1 equal to 1. Does that tell me that x sub 2 is this? And if I plug that into my calculator, here's what I get with my first iteration of Newton's method. Now, I'm so lazy, I use my ANS command on my graphing calculator, and I'm coming up with approximately this. However, if I apply Newton's method again and again, so second time, third time, fourth time, if I apply it the fourth time, I'm seeing no change all the way up to 3, 6, 9 decimal places. So I'm honing in on an approximation for the solution very, very quickly, within 9 decimal places, correct, just with 4 iterations. I only showed 1 iteration to the board, but on my calculator with my ANS command key, I can easily generate the remaining 3. Now there's an example where I literally gave you the equation to solve, but let's see if I can just put one last small tiny twist on this.